Okay everyone, Bismillahirrahmanirrahim. Welcome back. So here we are. We are going to do a sequential circuit design today. So before that, in the last week we actually started working on sequential circuits. We saw how to analyze sequential circuits. We saw how to actually build a state diagram from a sequential circuit. So this time we'll be doing the sequential circuit design. It's basically the reverse of the process of analysis. Roadmap so far is basically in this course we actually studied combinational circuits. We then saw basics of sequential circuit. We saw how flip-flops work, how different latches work, and then we actually started sequential circuits. Last time we actually analyzed the sequential circuit and saw how to analyze and build a state diagram from a sequential circuit. This time we'll be designing a sequential circuit, so it will be a process that is actually totally reverse of the analysis that we did last time. We'll actually start with the state diagram and end up building a circuit from that. Okay then, so sequential circuit design. So in the last lecture we actually focused on analyzing the sequential circuit. We found out the outputs and next state for all the possible combination of inputs and current states that is from the current circuit. This information is basically summarized into a state table and finally into a state diagram that actually represents the working of a sequential circuits. Today we'll be going to study some example of sequential circuits design. We'll do the totally opposite. We'll start with the explanation of sequential circuit. Then we'll make a state table or diagram to express the whole transitions, and then we'll turn that table into a sequential circuit. That will be the last step. So the whole procedure, the whole process of sequential circuit design, what steps to follow. We actually start with whatever the specification we are given. We make a state table based on the statement on the specification that are given. Then that state table that should show the present state, next states, inputs and outputs of the whole system. Then we actually in the second step we assign binary codes to all the possible states that we have got. So if we have got n states, the binary code will need at least log 2 of n digits, and that's because the total number of states that basically you need to give power the power of 2 basically as a total at the state elements. So we need this digits. We need for example, if you've got 9 states or 10 states in our system, we need at least 4 digits to represent those 9 states. So we have got 4 state elements or 4 digits for our system. So if you've got 4 state elements or 4 digits, it means a maximum of 2 raised to the power 4, 16 possible states can be done with 4 states, and that's how it is done. And for each flip-flop and each row of the state table, we find the flip-flop input values that will generate the next state. So for each state or for each current for each state, we have got the transitions that depend on the inputs. If you got a single input like the example last time, so it means a single binary input means we have got 2 possible options for a state transition from one state to another. That means that input value, if it's 0, it means that is one transition to a next state if the input is 0, and similarly if the input is 1, it will mean another one. So we know all the possible transition from the state table, and then after assigning all the binary codes, and those each digit will be actually be the state element, and that will be represented by a flip-flop. So if you've got 4 digits or 4 state elements, it means we need 4 flip-flops to do that work. Then we derive the simplified equation for each flip-flop inputs and the outputs, and that will give you the expressions to implement, and from that we build the whole circuit. So this is the whole procedure of building of or designing a sequential circuit. We start with a state table or state diagram, we assign binary codes, and then we set up the flip-flops inputs, and from those inputs we actually build the whole circuit. So for example, here we are actually going to look at an example, a sequence recognizer. What is a sequence recognizer? It's basically a system which has one input, one serial, a single serial input. That means it is basically changing value in every clock cycle. So here is your system. We can call this system as S. We have got an input X, that is your sequential input X. That means for every clock cycle this X will change value. And we have got an output. That output is, in this scenario, this is output Z, output Z. So that output will change its value according to our input scenario. So the scenario is here that it recognizes a specific pattern in the input. So for every clock cycle and the input changes, and it will be changing into a sequence. Now from that sequence we are going to recognize a specific pattern, and that pattern may be anything. So in this scenario, in this example, we have this pattern 1001. Whenever the input X changes its values from 1, then 0, then 0, and then 1 in a specific order, that means this will give you the whole sequence, the whole pattern is basically there. Whenever that pattern comes, the output Z becomes 1. So it means when the fourth element of this sequence becomes 1, the output Z will become 1 accordingly. So this is one thing. Similarly, the sequence can be overlapping as well. What happened in this scenario, we can see this is the first time the pattern comes, and when the last bit, that 1 comes, the output Z will become 1, and after that there is another pattern that starts from the last bit of the last pattern. So what happened in the second case, that pattern continues. Basically it's already in the first stage and it goes on to build the whole pattern, and whenever that pattern is complete, the output Z becomes 1. So this is the working of a sequence organizer. How to design this? Let's start the whole sequential circuit design process for this one. Right, so we have got one input X, one output Z. The system has a clock cycle C as well, so we can actually write a C here as well. So that C is basically changing, and for each clock, for each value, the X value changes as well. So first thing we have to figure out is precisely how the use of state will help you solve the problem. So this is basically the most the difficult step in this whole process. So what happens? A basic state diagram. Let's see how this works. So we've got a state A. State A is basically a stage, a point where our pattern has not yet started. So in this scenario, in this case, we can see here before the pattern starts, the whole thing, like in the first bit, you can see here when the value is 1. So what happens at this scenario? The pattern has not yet started. Similarly, or maybe you can say it's the first bit of the pattern, but the second bit has to be 0, so the pattern does not continue. It may be the case if we have got more zeros here. So you can say this 1 is already the start of the sequence, but if we have got 0 at the start, so that 0 means it's not part of your sequence yet. This 1 may be the start of the sequence, but this 0 means it's still not in the sequence. So for this basic state diagram, you can see this A is basically the before the sequence starts. Now if there is a one input in the system, so that means this is the first one. So we can see here that the pattern has started. So when the pattern has started, the state moves from A to B. So that B means that we have already got one bit in the pattern. We have already seen the first bit one. First one is already there. So first one is there. It means the pattern has started. We are now into the state B. What happens after this one comes? Again another one comes. That is something a problem. It means that we still do not have something to go to the next state. So if there is another one, it means it will stay in this state B. It will not move to state C. It will move to state C when the second bit, which is basically 0. So after 1 it has to be 0. If there is a 0 in as a second bit, it means it will go to the state C. So after 1, when it comes 0, and that means if we have got a pattern 1 0, it means we are in state C. Similarly, after that we have got another 0. If we have got 1 0 0, it means we are in state D. So this is the last state. We can actually this state diagram. From this state diagram you can see there are arrows, and on top of arrows there are some numbers. So these numbers represent the inputs and outputs. So this 0 means the number x, the input x, and this 0 after the slash, that means this is your output set. So that output is still 0. When the first input, first bit of the system, first bit of the sequence comes 1, the output will be 0. The second bit comes, the output will still be 0. If the third bit comes, the output will still be 0. After this D, this will be the point when Z becomes 1 if the pattern completes. So after D, what happens? There are two options. If the X input is 0, so after this there are two options. Either it will be 0 or it will be 1. So if there is, if it is 0, what happens? The pattern breaks. If we have got a 0, if we have got a pattern like this, 1 0, this is state B, state C, then state D, and after state D there is another 0. What happens? This means this pattern is broken. We don't have the pattern here, so it means it will go back to state A where the sequence has not yet started. So if there is a 1 here, that means our pattern is completed. Now what to do? So this is going to be the main thing. After this step D, state D, so if there is input 1, so it will complete the pattern 1 0 0 1. So it means if we have got 1 0 0 and then 1, it means it will be the output will become 1, or the pattern is completed. And the second thing, it will go back to state B. Why B? Because from this one it is basically starting another sequence as well, like what we saw in this scenario. The second one is basically the start of another sequence, another pattern of the same thing. So we are not going back to A from here because that won't matter. From D it will go back to state B because there is a new pattern that can start from this one. So after D we are going back to state B if there is 1, and the output will become 1. So these four transitions are basically when the sequence is going according to our plan. What happens to the other option of input X? We have got an input X. That means for each state there are two possible values. One is for the right state or the right pattern that is basically followed here in this example, in this state diagram. What if the input is different than the value? If we have got from state A, if we have got another value, X value is still 0. What happens if from A the value is still 0? So it means it will not move to state B because the state is not yet started. The pattern has not yet started. It will move only to B when the actual pattern has started. So if it is 0, it means it will stay in this state A. So if we have got the input 0, it means it will not move to B, it will stay in state A. Similarly, from B there are two options. If there is a 1, what happens if there is a 1? If there is 0, it means it's following the state or following the pattern, because the first bit is 1, the second bit has to be 0 if to follow the pattern. Let's say if the second bit is again 1, if we are actually having this scenario like in here, first bit was 1, the second bit was again 1, what happens now? The state should be again, it should be back to B. Why? Because it's still the start of the sequence. We can still start from here. If there is again 1, it will loop back, it will stay in this state B, right? So this is the second scenario, second input scenario for the state B. Similarly, if we are already in state C, that means the 1 0 pattern is already there. What happens if the third bit is not 0? So the pattern has to be 1 0 0 and 1, right? So what happens if the third bit is instead of 0, it is 1? So it means it has to go somewhere. The pattern is broken, so pattern is not going to complete. So what happens after that? From C it will go back to B. So it will be back to B because now it's again on the first step of the sequence of the pattern. So it will go back to B. That's the only solution for this scenario. So from C it has it either goes to D or it goes back to B. Now in D we have seen the first one case from D, the true case, if the pattern is going to be completed. What if it's 0? What if the pattern is broken at the last step? At this D it's not 1, and the pattern is not going to be completed. It's in fact 0 after D. So what happens then? It has to move to another state, and which state it should be? It has to be the state A. Why? Because the pattern is totally broken. Either it will have to start again from scratch. So these are the four possible all possible scenarios for each state. So we have got X input, so it means we have got two possible transitions from each state, one for the value X value 0 and the other for X value 1. And we have got a specific pattern that we need, that has to be there, and that is when that is the true sequence that we are going to see. And for that true sequence, if the pattern is recognized, that output will become 1. For all other cases the output will be 0, and the whole state machine will pass through these different states accordingly. So this is actually the state diagram for this sequence recognizer. These are the 4 states. So A, B, C, D, we have got 4 states. We have got X input and Z output, so 1 input and 1 output, and we have got 4 states. So for 4 states, how many state elements or how many bits we need to represent these 4 states? Because it's 4, we can simply have 2 raised power 2 equal to 4. That means we have 2 bits for each state. So this is actually the state diagram, state table from the state diagram, and we are just representing state A, B, C and D. So we are not putting the state digits here, bits or state elements now. We are just putting the values, the state names here. So present state A, if the input is 0, it will go back to either it will stay in state A, or if the input is 1, it will go to state B. Similarly in state B, for input 0, it will go to state C or if the input X is 1, it will stay in state B. Similarly from C, we have seen that if the input X is 0, it will go to state D because it's actually following the pattern, and from C, if the input is 1, it will go back to B because it will reset to the first step of the sequence or the pattern. And from the D, from the last state D, if the input is 0, it will break the sequence or it will break the pattern and it will go back to A. And if the D from D state the input is 1, it means it will complete the pattern and it will go back to state B, because this one actually can start another sequence because the sequence is recognizing this. So from this we actually, because we have got 4 states, for 4 we can have 2 state elements. From here we can use Q0 and Q1 as 2 state elements. We put 0 0 for A, 0 1 for B, 1 0 for C, and 1 1 for D. The 4 states they are represented by the state elements Q0 and Q1. So the same thing, then now this is done. All the state transitions, all these state transitions are basically now labeled in this table as the function of Q0 Q1, and the next state will be Q1 and Q0. The next values of Q0 and Q1 will be the next state, and we have got one input X and one input output Z, and that Z will only be 1 in just one scenario when the current state is D and the input is 1. So this is the whole sequence, this is the whole table, and that is your main thing for the designing of your whole sequential circuit. Now the next thing, because we have got 2 state elements Q0 and Q1, so we need 2 flip-flops, one for Q0 and one for Q1. And now the choice is yours which flip-flop you want to use. So there are different options you got. We can have a JK flip-flop. JK is one option. We can actually use any flip-flop. We can have a D flip-flop, we can have a T flip-flop. Every flip-flop has their own advantages. We can use any flip-flop whatever you like, right? So let's see what are the advantages and why we use JK flip-flop. Let's see how it works with a JK flip-flop. So for JK flip-flop, there are you know there are different options. For the whole characteristic table of JK shows that if both JK values are 0 0, it means it will be no change. Similarly, if we have got both JK value as 1 1, it means it will be a complement. Whatever the current state is, it will change to the different value. If the current state is 0, the next value will be 1. If the current state is 1, the next value will be 0 if both JK are 1 1. Similarly, if the JK are 0 1, it will be 0 the next state. Whatever the current state is, we don't need the current state, the next state will be 0. And similarly, if we have got current state as if we have got the JK value as 1 0, whatever the current state, the next value in the next state will be 1. So from now you can see we have got an option, we have got 2 options for each transition. From here we can see if the Q0 and Q0 values are changing, we can either use the 0 0 or 1 1 scenario. If we can use 0 0 or 1 1 if it's changing or not, or if the next value is 0, we can either use 0 1 as. For example, the next state, let's say Q0 has got value 0. Previously it was 0. So what are the 2 options of JK here? We have got JK values. We can use 2 different values of JK and still get the same result. So there are 2 options to get the same result from the current state 0 to next state 0. Either we can use the value 0 1. That means it will reset the Q0, whatever the previous state was, we don't care about that. The next state will be 0. It will generate 0 as the next state. That is one value. Or we can simply use both 0 0. Why 0 0? Because the last state was 0. We are seeing there is no change here. If there is no change, we can use 0 0 as JK input as well. So we can use two options according to our choice, and it actually gives us a choice of using don't care there. For example, in this scenario, k is a don't care. We can use any value of k and it will work. So if we are generating the inputs of JK flip-flop, the k will become a don't care in this scenario, and don't care are actually easy to implement for our scenario. So this is a JK excitation table after getting the after taking all these. If the current state is 0 and the next state is 0, it means there is no change, or it can either be 0 0 or 0 1. We can say k is don't care here. So if we are if the current state is 0 and the next state is 1, it means either you can have 1 0 as jk1 and j1 and k0, that is set, or we can have both j and k as 1 1 to complement the number. So this is how it's done. So for 0 0, it is jk 0x, or k is don't care. Similarly, if q is 0 and qt plus 1 is 1, we can have j1 and k don't care. So similarly, if current q value is 1 and the next value is 0, we can have j as don't care and 1 as k. And similarly, if we have got both values qt and qt plus 1 as 1 1, we have got j as don't care and k will be your 0 fix for this scenario. So this is actually the advantage of JK. We can have don't care, and those don't care actually work very well. Similarly, if we don't want to use two input for flip-flops like JK, we can simply use D flip-flop, and D flip-flop is very simple. Whatever, we don't need a last state value, we just see what's the next state value for each state elements, and we actually generate those from the flip-flops. So D, whatever the value of next state will be, it will be input of D. Similarly, for T flip-flop is for no change or change. So if T value is 1, it will be change. If T value is 0, it will be no change, and that will be very simple. These are the excitation tables for all flip-flops. Whatever suits you, you can use any of these flip-flops for your advantage. So back to the example, this was your main JK flip-flop input values. So we can see there are lots of X's or don't care here, which will make it very easy to implement using K-maps. And from K-map, we actually generated these values J1 and K1, and similarly J0 and K0. These are actually generated from the K-maps. That is simply because there is only one expression for that, so that is Q1, Q0 and X. So for all these other ones are just generated from the K-maps, and because of the X's or don't care, it's actually a very simplified version one. So from that, we build the whole circuit. This is the complete circuit with JK flip-flop to JK flip-flop that generate Q0 and Q1, and there are few inputs as well, some combination circuit that generates J1, K1, J0 and K0. And surprisingly, this is actually the same circuit that we have done in the last lecture. We actually started from this circuit and worked on building the state machine for that, so state table for that, state diagram for that, but it's the same circuit, and we can see it's simply a circuit with this specific state diagram that we started, right? So it's basically a simple sequence analyzer, and that we are actually generating from here. So what about the timing diagrams? Timing diagram is basically how we represent the change in the inputs according to the clock cycle. We see there is always the changes are done on the edge or positive edge of the clock cycle, so those positive edges are important. That where actually the output changes. So that's where we actually change the state of Q1 and Q0. And the output that does not necessarily change at only positive clock cycle, it can change whenever X changes. So since basically that is just dependent on Q1, Q0 and X. So if X changes, it will change to Z as well. So this is the whole thing, building the. Now we can do the same process with D flip-flops. So from JK flip-flop we generated the whole circuit. We generated J1, JK value, JK input for both of these circuits. So similarly, if we are going to use D flip-flop, it will be a little different, because every time the next state is basically which actually derives the value of current flip-flops, the D flip-flop for Q1 and Q0. So there is one D1 input that actually becomes Q0, and there is D0 that becomes Q0. So you can see here the Q0, whatever the value of Q0 is, that will be okay, sorry, this is actually just a little problem with formatting. Here we go. So Q1, whatever the value of Q1 is, that will be the flip-flop input D, and similarly whatever the value of Q0, that will be the flip-flop input D0. So from here we can actually generate whatever the values we are needing for these D1 and D0. They can be the function of input X and the parent states Q1 and Q0. So from here we actually generate the values of D1 and D0, which are the inputs of the flip-flop, and that we can actually get from the K-maps. And you can see here the inputs D1 and D0, they are not as simple or simplified version like we saw in the JK. So from JK you can see these these functions were very simple. Why? Because there were lots of don't care there, and that was the advantage, the main advantage of using JK flip-flop. For D flip-flop, it looks very simple, because we just need one input, one flip-flop input for each state element. So it's actually quite simple one. But for that one input, the expression will not be as simple as the expression for J and K. So these are the D1 and D0 expressions, which are simple but not as simple as J1 and K1, J0 and K0. So this will give you another circuit. The circuit is like we just discussed. This circuit is a little complicated, a little more complicated than the one with JK flip-flop, but because we just need one input D for each flip-flop, so it actually makes up for that. So this is the same circuit, but with a D flip-flop, the circuit is a little different, but it generates the same. It actually does the same thing. Similarly, we can do the whole thing using a D flip-flop. So flip-flop comparison, that's actually what we are just talking about. Flip-flop, JK flip-flop are good because there are many don't care values in the flip-flop input, which can lead to a simpler circuit that we actually just saw. We can see here for JK flip-flop, the circuit is very simple. We can have just two gates to generate J and K, but for D we actually saw three gates already to generate just one input D. So JK flip-flop are good because there are many don't care, and those don't care actually generate a very simpler circuit. For D flip-flops, they have the advantage that you don't have to set up different inputs, multiple input for flip-flops, but because there is just one input, the equations are usually more complex than JK input equation. Otherwise, it's actually the same. So basically, every flip-flop has advantages and disadvantages. You can use whatever you like. So in practice, D flip-flop are used more often because of just simple output or next state depends on D. That is the reason the D flip-flop are used, although the circuits are a little more complicated. So there are no excitation tables to worry about because we don't need anything. Whatever the next state is, the D input will be the same. That's why D flip-flops are preferred. So that's it. So the basic sequential circuit design procedure has 5 steps that we actually just studied. Make a state table from the expression from the state problem statement, and after that we can actually build a state diagram from that state table as well. Then second step, assign binary code to the states. We actually have to reduce the number of states first as well. That's actually very important task. We have to keep the states as minimum as possible to get the complete work done, and then assign the binary code to the states. Those binary states will actually give you the number of state elements. Use the present states, next states, and flip-flop excitation table to find the correct flip-flop input values, and then we simplify the circuit using K-maps, and after that we build the circuits. So that's it. That's the whole procedure of building sequential circuits. From now we'll actually study a few different sequential. Next few sessions will be comprised of different examples. We are going to design different circuits, so just get ready for that, right? So over to the next time. So see you then. Okay, bye bye.